Hello, this is going to be some chill maths. I'm James. We're going to be trying to understand quadratic forms. We're in chapter 5, the classification of quadratic forms. Had a bit of a stab at it a few weeks ago. I'm back. Now we're going to have another go. Hello, maths 2222222. Good to see you in chat. And shout out to somebody's followed me. Not while I'm live. And people usually follow when I'm not live. And then unfollow when I'm live. Shout out to, I've been practicing before the stream started. I'm pretty sure their username is Meredahu Latans. I think I nailed it. Meredahu Latans. There you go. Classic Meredahu Latans. 7 syllables. They make it too many tricky. They make it tricky for me. I can't even say this one with all the twos in. There was one bonus one at the end. Right, good to see you again though. What are we doing? Well, according to the what command in chat, if you type !what, which I've just updated, then we are back on Hatcher's Topology of Numbers, which is a textbook that I am. This year, most of my Sundays when I'm live, I am trying to read this textbook. I've left myself some notes from last time I see, which don't mean anything to me right now. So I'm going to do some catching up. And then we're going to do some stuff to try and get it all in the old headspace. Hey Murray, how you doing? Good to see you as well. Hello Herb, there you go. Good to be back. I had a week off last week for the Maths Festival, which is a big event in Oxford where we do one day out in a shopping centre and one day back at home in the maths department, and we have hundreds of local families come along and do some maths activities with us. This year, including a giant squashy Soma cube. I don't know if you're aware of this puzzle. I'll show you the Wikipedia page. Wikipedia knows that I love this page. It's flagged it as you visit often because I get here all the time. The Wikipedia page Soma cube looks like this. It has 7 pieces. All of them are made of 4 cubes except for this little L piece, and the puzzle is to assemble them into a cube. We've got quite a few of these small puzzles, but this year we also now own an enormous squashy soft play one, which you can build forts and things with, or even build a cube. So that was my weekend last week, which is why I wasn't live last week, because I was, for part of it, trying to get children to assemble one of these, but about a metre by a metre by a metre is huge. Great. I think we should get more soft play equipment in the maths department. Maybe some more inflatable decorations and things. It's great fun. I'd be up for more theming, I think. Maybe this textbook could do with some theming as well. That'd be fun. Palm trees everywhere. It's always palm trees for me because I've realised, left to my own devices, I will make absolutely anything pirate themed. There are multiple logic puzzles that we have at the Maths Festival, and they needed a refresh, and then afterwards we looked back at what we'd done and we realised that I had added pirate theming to 2 of them, which, there you go, yes. Math City in Leeds, yes, very good if you're in the area. They're great. I've never been, but I've seen loads of photos of it. I'm pretty sure they have a big squashy Soma cube. It's a thing you can get, and it's definitely maths. Yes. Wait, what? Is there one of these cubes in a Zelda game? That would be amazing. I should use this to tell children about maths, right? Which one? If you can remember which one, I would have enjoyed it. Especially if it's one of the modern ones, because I think kids these days are more likely to have played the modern ones. Right, inflatable. You could make some of these diagrams down here out of balloons, right? These ones, they could be like, I'm not very skilled at balloon animals, but I reckon you can balloon. I suppose the tricky thing here is that we're trying to label the regions. Tears of the Kingdom has got a Soma cube thing. What? Gotta Google this. Is it worth? Okay. More research needed, I think. But possibly they have something you have to build out of pieces. And the pieces might be Soma cube pieces. They look a lot like Soma cube pieces, actually. I'm looking now at a thing on my other monitor. Oh my goodness. Possibly, yeah. That could be precisely it. Oh, wow. Okay. This is finally how we're going to connect kids with maths puzzles. You already did one in a different thing. Right. Yeah, no, I trust. I realised midway through, what am I saying? I trust Mary on this too. Right, good. Okay. Can we pirate theme this? What are we up to? I remember we've got these diagrams, which form this sort of an almost binary tree, which is connecting together. Is the binary tree connecting regions? I can't remember. Possibly the binary tree is connecting. Yeah, I feel like it's connecting. No. What does this diagram mean? Oh dear, we've gone quite basic. I think the fractions. I remember there were some fractions or pairs of numbers that you could put into a quadratic form because it takes x and y when you put those numbers in, and they're labeling regions. I remember. So I need to stop thinking about my. I would have thought about putting fractions around the outside of the circle or something. So we've had this thing about putting medians in, but those now correspond to regions. The regions are connected. I can do this. The regions are connected if you have a sort of median rule. Right, so two regions would then go to the next one, putting in the median fraction. Okay, right, so there's a bunch of regions on there. Let's try and draw some regions. So there's all of this going on, where each fraction I mark the midpoint. There's a rule for what fraction I write there, which I'm not too excited about right now. I'm trying to remember the structure, not that. And then each marker, I'm not trying to connect to the marker, I'm trying to give it some area nearby. So I put this midway marker in. No, that one belongs to this whole region. And then I put in some more regions and some fractions down here. And then the binary tree, right, the binary tree is the connections of these regions. No, not quite right. Not quite right. Ooh, I've really forgotten how this diagram works. That's a problem. Yeah, we have lots of diagrams. At one point we switched, I remember at one point we switched from looking at the graph to looking at the dual graph, and I found that very confusing ever since that happened. So it probably is worth me spending 5-10 minutes on the front thinking about SOMA cubes and also thinking about what on earth all of our diagrams mean. We're definitely plugging in values. You made me that Desmos thing a couple of weeks ago to show me fractions from the outside, plug in those values. So what are the edges? Edges then. Yeah, okay, I want to go back. Yes, all this sort of stuff, right? All this sort of stuff. Right. Back up. This is not too bad. I know we're going back. We want to go forwards. We're going back, but got to go backwards to go forwards sometimes, especially after a couple of weeks of not looking at the thing. Right. Okay. What are these? Is this going to tell me, or do I have to go back even further? I think I do to remember what how the topograph works. I'll see it and then I'll remember, and then I'll say how it works, and then we'll go forwards again. Yeah. So all these lines dividing regions. This was the separator line. So the regions correspond to fractions or pairs of numbers that you can put in. Here's a diagram. Don't like that one very much. Yeah, okay, fine. You can put numbers in. Yes, Desmos. Yes, please, Desmos. Because of the layout I've got, you can see if I need to drag something from chat, you can sort of infer where stuff is, I suppose. The chat is over here somewhere. And the place where things get loaded before appearing on the screen is over on the left somewhere. I'm not actually that happy that you can infer the entire layout of what's going on from things just sort of wobbling around screen like that. Oh well, okay. This is the fairy diagram. Thank you very much. That's 222222 in chat. I said it carefully that time. He built this. Okay, so what were the lines? I've gone really basic on this, sorry. Oh, so this is... Yep, okay. So, I'm getting there. The picture on the front of this textbook has got... Here we go. The picture on this front of the textbook Oh, we drew it on the top. Oh, there we go. I drew it on the front of the book. Good. This is the diagram we needed. Okay, good. Almost there. Yes. So, the colourful blue and purple stuff, we thought about these for ages. I think they are the regions that you get when you join up fractions. So we started with a fraction over here. I think it might have been 1 over 0 on the left and 0 over 1 on the right or something like that. Oh, you can switch on the fairy diagram on top. Whoops, it should probably just be in Desmos. Okay, so we get lines connecting things, and then you join the lines to the mediant. And then the brain melting thing I'm trying to imagine is, what does that do to the connections for the areas? Because when you draw the first line, you get 2 areas, one here and one there. And then, crikey, when you draw in this new pair of edges, you're splitting up some areas. You create 2 new areas, which is also where you will write the next fraction, right? Next fraction is going to go here. Is that right? Yeah. Oh no. So the next fraction is going to be written here. I think it's 2 over 1 or something like that. Maybe 1 over 2. You write the fraction here, and then that corresponds to this area in here. Not that point, but this area. Yeah, okay. So it's valued when you plug in 2 and 1 into your quadratic form, gets written in kind of this part of the graph. Okay. So the edges then are connections between areas of the front page of this book. The vertices of this graph, the top of graph that we're looking at, correspond to areas on this diagram. And the area, but not right. But areas on the fairy diagram are not regions around the outside of. Yeah, okay. They're kind of quite closely related, I think, but the region around the outside is associated with that fraction. This point here is kind of not associated with the fraction. It's associated with the area, which is connections between 3 of the fractions, which you could probably rephrase somehow. Good, right. Okay. Let's go and have another look at the Desmos, because we like that sort of thing around here. You told me you can switch on fairy diagrams on here. So let's click on off. What do I want to see? Yeah. Do I want to see fairy diagram? Yes, I do. Thank you. Good. Okay. Right. So green lines on here join together. Well, initially they join together 1 over 0 and 0 over 1, and then they join 2 numbers to the median. Whenever you write in the median, it was 1 over 2. Whenever you write in the median, you draw in those lines. You get an area, and then you get, so I haven't quite got my head around this, you get these pink lines joining the regions. So can I think of that area? Can I think of part of, what I'd like is, we've gone from areas to edges to areas again, and I'd like it if they had turned out to be the same areas, and I'm a bit worried that they're not, but maybe I'm worrying too much. So each region bounded by these pink lines, does that correspond to a region of the bounded by green lines? I think there is a matching between them. But in each case, you can go to the furthest away, the node that's the corner vertex that's furthest from the boundary. I will get my words right. For each region bounded by pink lines, I think you can uniquely go to the corner that is the furthest from the boundary, and that lies inside some region, which is exactly one of those, and then it branches outwards. So you go out that way, you get a region, and you get this. Yeah, okay. Edge point. Yes, that was a doorbell, but it's fine. It's fine, they'll come back. Good, right. What are we going to do? What does that say that? We've sort of taken the jewel of the jewel, which should get me back to where I started. So now, okay, now I'm happy again, I think. So when I'm talking about putting the values in, we don't do this in the book, or I haven't seen this in the book, but it feels like I could push that value. So this, push that value up to the point. Oh no, Herb, what happened? Herb, what happened? Herb, what happened? I entirely missed why you got timed out. Oh, you got timed out for the one reason. The one reason that people get timed out. It hasn't even been working very well on bots recently. I have a rule about that's supposed to counter bots, but only actually counters real viewers and no bots at the moment. Sorry, Herb. Yes, right, I see. Yeah, you have to be very careful when talking about people who are watching a thing. You're advised to use a long phrase or random diacritics on top and underneath your letters. Either works. Twitch, eh? What's that like? Right, okay. Yeah, can we invent a different word that a different synonym? Right. What am I doing? I'm going to go back in to page about 130 or something. I've gone to the front, you see. But somewhere around there? Seems like a good place to jump back in. I'm going to do my best to try and catch up with what's going on with the classification of these quadratic forms. So you see, I've got these regions, but I still think. I suppose if we go through the separated line, I shouldn't say stuff like the furthest point from the boundary. We're trying to do topology or something, so we won't know which one it is. Yeah, okay, so we have this thing called the discriminant, which looks very familiar based on values b squared minus 4ac, abc from the quadratic form. Okay. And we did some work ages ago. We read this bit to work out some stuff about identifying which type you're in. But now I think we're trying to classify which ones you can actually do, or find all of the possibilities. We've decided that they might be equivalent to each other if they take the same values. I think that's right. And there's some rules like if it matches at a point with the three areas around, then it stays the same from there. I think watches is safe for now, but sounds weird. Ice cubes. Oh yeah, I still my ice cube theming, don't I? I'm gonna lean into the ice cube stuff and the observers. Amazing. Right. It's already alright. Okay. Good. I remember we're looking at a calculation somewhere in here. Yeah. Okay. Here's the equivalence of forms about we had delta and we were adding on numbers and trying to make things we could factorize sort of finitely many possibilities. I'd like to see that again, I think, because I remember it being interesting, but I've forgotten what it was. Okay. So equivalent forms, here we go. Look the same. Quadratic forms are equivalent. No, so so the forms are equivalent if they, well, it does turn out to be if they. I want to say it's if they take the same values, but it's if there's a vertex where they take the same values. From there, you get the same values. Everywhere else, is the converse of that all right? Portuguese. We had someone on the Thursday Maths Club show at work who speaks Portuguese, and I think it was Mary in chat posted it in Portuguese, and I almost tried to read it out, but then realised that I couldn't because I don't speak Portuguese. That was some fun. You know when you realise that. Realise like, hang on, oh no, actually that's not a skill I have, of course. Right, good. Yeah, so maybe I prefer this linear fractional transformation Mobius map sort of thing. Same with the first definition. Since if you can take it over there with an LFZ, then you get the same values. Could I take the same values but in like totally different places? Is that a thing? I would like to keep saying takes the same values, and if pushed, what I really mean is it has LFC. Like this, you can transform it so that you get the same values of a particular vertex and then the same values from there. We've got a method to extend outwards what values we get because of the arithmetic progression rule. Yeah, I think that's right. For me, the important thing about that is that they take the same values, and I try to work out if the converse is true. I'm a little bit worried that you could have something which took 1, 0, and 2 at a point, and a different one that took 1, 0, and 2 at just random places, and they could turn out to take the same values without being equivalent. In fact, maybe that's important because maybe there's ones that could take all values that are sort of not equivalent because they take them in different places, not the same topology of being connected where they take the same points. Okay. Mirror images are fine. Since, yeah, okay, we're not worrying about the order that you take the values around a vertex. What about these things where you can take the same numerical values but in different places? I'm not going to worry about that right now. Okay. These are always equivalent. Why are these always equivalent? So the values, let's think about the values. This one, if you plug in, we've seen this before I think, but if you plug in 1, 0, you get A in both. If you plug in 0, 1, you get C in both. And then if you plug in 1, 1 or 1 minus 1, so I'm plugging in different numbers, I'm looking at different, let's see if I can get it in my head. So I'm plugging in different numbers, which in the green line fairy diagram would be an area, which means that there's a vertex there on the top graph. So I'm looking at that vertex. I'm looking at different vertices in the different cases. It's a reflection across the x-axis, I think. Yeah, reflecting across this horizontal axis. Okay, good. I know I read that before because I've been here before, but I'm pleased that I'm getting more of an image. It's good. Yeah, I think so. Yeah, so hang on. Okay, so question in chat. If you change the order of the coefficients, so instead of ax squared plus bxy plus cy squared, I would hope that this is the same, right? Or considered equivalent. And what do I need to do? I need to find a vertex, oh, hey, on the end there, a vertex in the first one where the numbers around it are the same numbers as possibly a different vertex in the other one. Gosh, that's a mouthful, isn't it? And looking at the values around a vertex means choose two numbers and their median, which is where you add the numerators and denominators. Take two numbers and their median because that corresponds to green lines in the fairy diagram with nothing else weird going on in between. So an area, so a vertex. Right, okay. So in the first case, I'm going to plug in easy things like 1, 0 and 0, 1 and probably 1, 1. And I'll get A, C, and A plus B plus C. And in the other case, I will plug in, yeah, the same numbers, and I'll get the same values in a different order. Yeah, so I think that vertex, you get the values in a different order for between these two, but that still counts. I think that might be some sort of reflection in the y-axis in terms of the values on the top of the graph. I think, yeah. Okay, good. I'm gaining confidence, which is why we stop and think about things, is to try and gain confidence. That is a terrible picture. Least circular circle. Okay. And then there's more complicated ones where you might discover that plugging in, I've got to say a fraction like 1317 and some other stuff gives you the same values as you would have got in a different quadratic form by plugging in simple values, which seems quite hard. It feels a little bit like, thematically, it feels a bit like completing the square or something, to find some way of plugging in numbers to get, for that particular one, what's the minimum or something. What do you think about minimum? Sometimes. Right, okay. What on earth is going on over there? Right, good. Okay. So then we're talking about elliptic forms. Here we are. Every possible elliptic form. This, like this, we did some rearranging or something. And if you tell me the discriminants delta, then there's a relationship, of course, with the coefficients. Is there a way to slowly move a quadratic form towards a specific value? I don't know what moving a quadratic form means. If you have a value in mind that you'd like your quadratic form to take, then I'm going to find out in a second whether or not it takes that value. I suppose what's the strategy going to be? Something like, think about the minimum value, look nearby, work your way outwards, or find the separator line and work your way outwards from there. It's periodic, so it should be okay. Oh, that's quite clever. Okay. Right, what happens if you transform a quadratic form so that the centre point don't know. What happens if you send it over there? Well, I suppose if you just transform it so to take the values over there, you'll get a more and more complicated looking quadratic form, but maybe this is good, that when you plug in complicated values you get more, and the complicated values you should plug in could be x and y close to having ratio √2 if you wanted them to. What are we trying to do there? Because that's considering changing the quadratic form. Whereas I think I'd like, what would I like? I would like points that are quite close to √2 because I'm interested in rational approximations of √2. I feel like we've already got that with where is √2 on this chart and what's near √2. I suppose, yeah, given a quadratic form, I'd like to know where it takes low values like 0, or if it does that, or 1 if it can do that. I'd like to know which values it takes. Yeah, I'm not sure I want to move the centre point, intentionally move the centre point somewhere else. I quite like the idea of always moving the centre point to somewhere nice and easy. That might make things equivalent. I'm sure if you have this transformation that you could use to move the centre somewhere else. Maybe I'm wrong. Oh, right, find a different equivalent quadratic form. Close that vertex. Yes, we have these transforms, right? We have these transforms to, I can't quite remember how it works, but we have these transforms to move things around. Pivot, sort of pivot around infinity to move the graph around. And if you do that, then, well, how does that change your quadratic form? Yeah, I guess I'm suggesting we do some sort of composition between the thing that moves stuff around in the fairy diagram. There's a transformation for that, and then evaluate your quadratic function, quadratic form. So, what does that actually look like? Don't know. Right. Okay. You see, this is what happens as well. We also get people putting diacritics on, and then I have to go and manually ban them. How do I even do this? Do I click? I do click. Yeah, it's not FetterWeb, is it? What an incredible username. Great. Okay. You can move the centre point anywhere since the -1/x value will go to the other centre point. Now I don't know what that means. I thought there's only one centre point. Okay, right. I'm going to reread this bit of book, and then we're going to find out if there are any transforms that move things around and move the centre point somewhere else. I will get there when I get there. Right, okay. Now I'm concerned that I didn't understand chapter 4 either. It's possible that I am standing on a wobbly pile of mathematical understanding that can come crashing down at any moment. And the best thing is, after it's come crashing down, I won't even notice. I'll just stay there in the air. This all looks fine to me. Right, okay. Join me at the top of this wobbly pile, and let's see some large numbers. Hooray! Here's the case, with 260 in it. What are we looking for? We're looking for numbers to put in our quadratic form such that it might have discriminant 260. We think that studying all of the possibilities for a particular discriminant is a good idea, because if they're equivalent, they've got the same discriminant. Is that clear? There's some relationship between the values that you have at a point. If you know 3 values, then you can use the oh goodness me, if you know 3 values, so if you know 3 values, then there's a rule for working out what's going on over here to say that it is twice a plus b minus c, so that the difference is the same from between the sum of these two and c. That difference is then repeated over here, and then from there you can work out this h thing, which is a quantity that kind of belongs to the line, which is the difference. Goodness me, what's here the difference of? How does h work? Oh, I can't remember these edge label things. Oh, is it the common difference of that arithmetic progression? So it'll be a plus b minus c. Oh, good. Here we go. So once you know h, is that good? Oh my goodness. What am I doing? What am I doing? Given 3 values around a point, which is how you determine that things are equivalent if they have the same 3 values around a point, because then you can infer everything else like that, using that rule to go through the binary tree from there, branching away outwards to fill in all the numbers so they'll have the same values. I'm trying to claim that these have the same discriminant, and I'm not really getting there. Oh yeah, so there's some relationship between the discriminant, this is important, isn't it? There's some relationship between the discriminant and h that I have forgotten. Is it on the screen somewhere? No. Can I work it out? Yes. Yeah, probably. How convinced am I by this? So it would be equivalent if we moved it somewhere else, and then we could work out the coefficients in the quadratic form. I don't know. Yeah, there's loads of transformations though that move these points absolutely everywhere. It's complicated, right? How am I going to do this? I know it's in the book somewhere, but I think it's a sort of challenge for me, testing my understanding, to work out, if I know the values, it feels like I should be able to work out the coefficients. Let's quickly try and do that. Can I scroll sideways? Oh yes, I can. Perfect. So something like, I would like to know A, B, and C. I believe that this is true. Is this going to be a mess? No, this is fine. I don't know what numbers correspond to this. I just know that at some point in my diagram, I've got 3 numbers around a point, A, B, and C. It's labelled with the arrows coming out as if it's a sort of centre point, a source vertex or something. Oh, maybe those are different things. Maybe that's why I'm confused. Okay, forgetting the arrows and the directions. I'm not sure I like this lowercase c, this lowercase h thing at all. So then I'm sort of going, well, I'm trying to go to the median point, right? So I think that would be x1 plus x2 squared plus b, x1 plus x2, y1 plus y2 plus c, y1 plus y2 squared. Given those, can I solve for lowercase a, b, and c? No, of course not. I don't know the values of anything, do I? Seems daft. oh, can I solve for the value of b squared minus 4ac? That sounds more plausible. Still a bit daft. Yeah, although, okay. Yeah, this seems a bit daft. So if I know these three values, then the result is something like you could transform it to move this to the origin, move this to a simple point, plug in those numbers and work out the discriminant. I'd like to do it directly. I want b squared minus 4ac, please, in terms of ABC. Is that possible? Can I do that? I don't necessarily need to know the values of lowercase a, b, and c. In fact, I think I probably can't work those out, lowercase a, b, and c, because there are lots of different equivalent quadratic forms where I might not be able to find those. But it feels like given this much information, maybe I can work out the value of b squared minus 4ac. Because I have this sort of belief that the discriminant should be the same for all of these. This doesn't look doable, so I'll be sort of surprised if it falls out. Although that said, these are brackets that are multiplied together. That said, I suppose when you multiply things out, you get quite a lot of familiar things, and then some horrific cross terms. So maybe I'm into that. Maybe not. You know, I multiply this square and I'll get these terms, but I'll also get all of the cross terms. I don't know about that. And they don't make me happy, they make me cross. So, cutting some corners slightly, when I do the square, and I do x1, y1, and this square over here, maybe I will get capital A. Is this going well? No. 2a x1, x2. I don't like that. And then over here, b x1, y2 plus x2, y1. Don't like that either. And here, 2c y1, y2. But I will pick up terms for b. I've got these square terms. So there's cross terms. Don't like them. And that goes over there. Yeah, don't love it. What am I doing? What do I want out of this? What am I trying to do? I was hoping this would fall out and just tell me the value of b squared minus 4ac. It hasn't really done that, has it? Why did I think that would work? Right, okay. What do I think? Oh, worse. These points are not just random points that I've joined up with their mediant. They also have a line going between them. So I've joined them to their mediant, but they have a line between them, which means something like, so these things, there's like some line between them in the fairy diagram, which means that is this thing I'm always saying, x1, y2 minus x1, x2, y1 is 1, I think. Is that helpful? Doesn't seem unhelpful. In the sense that it's a fact about all of these things being related to each other. Seems impossible that you can infer the discriminant from these three values, and yet it sort of has to be, because if it's true that you can transform it, there's some transform that moves it to a simple point such that these are just the values when you plug in 1, 0, 0, 1 and 1, 1, then you get the values, well, after moving it, these with values when you plug those things in. So if it were the case, then the discriminant is this. I don't really believe in this h thing. So if I want to get rid of h, then I have sort of h is, if this is b, then h is supposed to be something like, in terms of my values, they're in lowercase over here, which I don't love, but they would be a plus c minus b. Which is sort of sum of 2 minus a third, which I've kind of got going on over here. So don't mind that. And then the solution is apparently that the discriminant is that thing squared minus 4ac. Which, so if you give me 3 values, I am told reliably that the discriminant of the quadratic form that gave you those 3 values around that point, ones which were each connected by lines in the fairy diagram, with a dot for a vertex indicating a region in the middle, that what's going on there is that the discriminant is a plus c minus b all squared minus 4ac. Seems a bit odd. Oh, that is not too bad, right? That's a squared plus b squared plus c squared minus 2ab. Oh, this is not too bad. Minus 2cb, bc, and then I would say plus 2ac, but minus 4ac here. So it's nicely symmetric. Of course it is, has to be, because the 3 values, where you think that changing the order of them should give you equivalent forms. Okay, getting somewhere. Still not there, but apparently. So over here, these are values. There's a bit of a notation disaster going on between left and right of this line. Left, there are lowercase letters for values, and the discriminant is supposed to be this combination, sum of squares minus those. That's the discriminant, the kind of b squared minus 4ac thing of the quadratic form that gave you those values. And I should be able to prove that just by looking at these, but it hasn't fallen out yet. And I think I'm about to break symmetry, which I don't enjoy doing, because I have a minus sign up here. Should I be squaring everything? So an approach open to me that I don't particularly want to do is something like I square these, because these are the values, and I also multiply pairs of them, and then it should just fall out that I'm left with b squared minus 4ac multiplied by some horrible thing that happens to be equal to 1 because of this rule. Yeah, not a disaster, right? Not a disaster. I can't really see how the b squared minus 4ac is going to come in, though. Where's it going to come from? I could break symmetry here a little bit with this 1. That will give me a b, and then kind of 2 of these in some combinations mixed together. Should I do all the squaring? I could do all the squaring. Oh, it's like 9 terms each time. They're bad terms as well. There's some real mess that would come in here. How can I do this better? I'd just like to work out that the discriminant of the quadratic form that gave me these numbers, the discriminant of the quadratic form that gave me these numbers. So sort of a change of variables is one way to think about this transformation, right? That some sort of change of variables, which then says if you have numbers that do this, then there's a different quadratic form. Yeah, so maybe the more direct proof is to check that when you do these sort of transformations, LFZ, linear fractional transformations, they're calling them in this book, that it doesn't change the discriminants. I feel like that might be in the book. Could just square everything, generate so many terms. Really, so many terms. Almost unimaginably many terms. If we calculate this expression with using these capital letters, where I've just naively plugged in values of unknown, I don't know where this point is, but unknown point. So I'm looking for a better way. What happened over there? Oh no, that was normal. That was part of the A business. I could square this thing down the end. Do I want to do that? It should then be the case that I can just multiply. So mine has got A and B as the pair. This has got A and C, so I should then be able to just subtract the 9 terms that you get from a product of these things. Do I want to do that? Not really. Not really. Yeah, let's go for it. How bad can it be? B, shall I also do the switch? I think I also will do the switch. But this x1, y2 business is plus or minus 1. Maybe that does need a square on it. Let's keep it all for now. Plus 2c y1 y2 is equal to, and then no regrets yet, this c minus a minus b. And following the logic from before, if I square this and then subtract 4 times ab, possibly I'm left with, astonishing, I'm left with exactly the discriminants I want. So we're going to work that out. There are going to be many terms. Can I scroll any further? No. There are going to be many terms from squaring this. We're still going to subtract some more terms, 9 more. Okay, so there's 9 things minus 9 things. I should just do it, shouldn't I? So you square the first one. You square the second one. You square the third one. And then you get the cross terms from doing all your squaring. So you get 4ab x1 x2 bracket stuff. You get the cross term from multiplying the bracket by the other thing. Let's do that one next. y1, y1 y2, x1 y2 plus x2 y1. And you get the cross term, which has got 8 on it because it picks up both of the 2's, x1, x2, y1, y2. Oh my goodness. Those are the cross terms. 1, 2, 3 square terms, and those cross terms. Not really 9 things because I've collected like terms. Good. And I'm interested in 4ab, which is 4 times, and this one had the x squareds in it, x1, y1 stuff, sorry, cy1 squared times a x2 squared plus b x2y2 plus cy2 squared, which is, okay, there are going to be about 9 terms on this, and hopefully lots of them are going to cancel. Seems a bit unlikely, doesn't it? But hopefully lots of them are going to cancel. I can already kind of see that this 4a squared, x1 squared, x2 squared is going to cancel. I get that off the very first thing. And similarly for the c squared, y1 squared, y2 squared. And can I look even further into the future of how this cancelling is going to work? Well, I've got some AC going on here. x1 squared, y2 squared. Don't love that. Yeah, don't love that. Can I see any other good cancellation? Not really. Not really. Off we go then. Let's just do AB for now. We'll think about factors of 4 afterwards. I don't want to write loads of 4s. Equals. Let's go all the way over here. So I get this a squared, x1 squared, x2 squared. That's nice. I get some AB stuff. How much AB stuff do I get? Now, of course, I want this much AB stuff, probably, because my discriminant expression shouldn't have AB in it. It should be b squared minus 4ac or something. So I don't really want this. I don't mind a bit of that. I don't mind a bit of b squared, but I don't want these to hang around. So I'm hoping that this AB stuff doesn't last long. and it's going to look like x1 squared x2 y1, and also I'm going to get the same thing with the 1s and 2s the other way around. Is there a fast way where I just... Okay, we'll come back to that idea in a second. Is this going to match up? So over here I've got x1 squared x2 y2, 1 squared x2 y1, bother. Okay, so there's 2 down here. I'm getting my subscripts wrong. 2, good check, good process. Right, in here I get x1 squared x2 y2, that's this, and I get x2 squared x1 y1, that's this. So that is going to cancel with the 4, perfect. And then I'll get some AC terms as well, and they'll be pretty similar. There'll be things like y1 squared x2 y2 and y2 squared x1 y1. That's actually a BC term as well, because I'm doing the same sort of cross multiplication. And comparing over here, I get y1 squared x2 y2, and I get y2 squared x1 y1. So that's going to cancel as well. Good. If you're playing along at home, then, oh my goodness, sorry. If you're playing along at home, I haven't quite got all my terms. I've got 1, 2, 3, 4, 5, 6 terms, so 3 more to go. Yes, including the b squared term, which I like. And lots of things are cancelling, except for some b squared stuff and hopefully some AC stuff. Those are my remaining terms. So my b squared term looks like x1, x2, y1, y2, that's pretty nice. And my AC term looks like x1 squared, y2 squared, plus x2 squared, y1 squared, catchy. So I'm hoping that with the factor of 4 in, when I do this cloud of stuff minus 4 times this long line of stuff, that I get some b squared terms and I get some AC terms and nothing else. And there's some cancellation over here with the a squared stuff, and some cancellation over here with the c squared stuff, and I hope I've convinced you that the ab and bc terms also cancel. So I'm going to be left with b squared times, now over here I get x1 y2 plus x2 y1, that's all squared, but then we're subtracting 4 lots of the cross product in the middle, x1, x2, y1, y2, they're kind of critically pair of products, which then factorizes again. So c minus a, let's go for this. This is like my last line, I think. If I take off 4 of those, then after subtracting, I'll have a negative sign. I'll get plus 2 times this cross everything, minus 4 times this cross stuff down here. So I'll refactorize it, which is perfect because that gives me x1 y2 minus x2 y1 squared. Oh, hello, Lazjema, good to see you. No tea at the moment. We're about to get to 3 o'clock, and I'm about to get to the end of this calculation, so it's all looking good. This is perfect because this thing in brackets is plus or minus 1 from the rule that I wrote somewhere miles up there thinking about the connection in the fairy diagram. Ooh, yuck. Right, what else do I have? 8 AC, which is kind of way too many of them. And the AC terms currently look like, oh no, let's put 4 AC out here. And it's looking good, it's looking strong, because for AC in here I have 2 x1, x2, y1, y2, and down here after I've subtracted 4 lots of this AB thing, 4 lots of AB, down here includes these, so bringing out the factor of 4 and the AC, I get minus, sorry to wave the pen around so much, minus x2 squared, y1 squared, and that looks a lot like the same thing, the square of x1, y2 minus x2, y1. You get the square terms and you get this opposite signed thing in the middle, so that's the square as well. But I wanted a minus sign, which is good because there is a minus sign on all of these, right? When you multiply out a square, you generally get positive squares, and this thing has minus signs on. So this is b squared minus 4ac. Okay, I don't know how I would have spotted that this combination of capital A, capital B, and capital C gives me the discriminant. But the thing that I've convinced myself of now, which probably in the book, probably read it last week or something, I'm sorry, but the thing I've convinced myself of is given 3 values around a point, not thinking about arithmetic progressions or differences or anything like that, but given a little bit of this fairy diagram, or whatever we're calling it, think about regions corresponding to plugging in pairs of numbers. If you give me the 3 numbers that you can see around a point in this diagram, then I can work out the discriminant of the quadratic form. So let's see, have I still got that Desmos? I've still got this Desmos. Thank you for making these Desmoses, maths 2222222. So here, I'm not looking at the left of my screen where it says what the quadratic form is, I'm looking at the values. So I choose a point like this one in this binary tree, which connects regions of the fairy diagram, and writes numbers associated with plugging in the numbers. So I can see that this quadratic form, I'm not looking at the formula on the left, if you plug in the numbers 0 and 1 in this case, you get -3. If you plug in the numbers, what's that down there? That'll be -1, 1, you get -2. And if you plug in -1, 2, you get -11. So, without thinking about where this is though, just saying, oh, you've plugged in some numbers, without knowing these numbers, so if this gets transformed, so this is actually somewhere else in the diagram, you'll get different numbers in your quadratic form, be a different quadratic form, but this combination of seeing that it takes values -3, -2, -11 means that I can do a calculation, which is maybe best phrased as the sum of the squares minus twice the sum of the pairs. Sum of the squares minus twice the sum of the pairs. That's what it says up here. Sum of the squares minus twice the sum of the pairs. The dissimilar pairs. I could do that calculation on these numbers and get a discriminant. Shall I do that? I could probably do that. Can I do it in my head? 121, 9 and 4 is 134. Sum of the pairs is 33, 22 and 6, which is 51. Beware the minus sign though, there are several. 33, 22 and 6 gives 51. So I've got 134. I'm supposed to subtract twice the sum of the pairs, but the sum of the pairs is negative 61. 55 and 6 is 61. Subtract twice that is 122. So I started at 134, I'm adding another 122, I get 256, or something like that. 256. So I think for this quadratic form, up to a plus or minus sign, because I've been a bit worried about those, its value of b squared minus 4ac in that quadratic form might be 256. That seems quite large. Where's the quadratic form in here? Oh, it was not on screen. Okay, I'm miles off. Its value of b squared minus 4ac is nowhere near that, right? Oh yeah, so my squares pairs are positive. Yep, okay. Minus times minus is plus. So I should be doing 134 minus. I should have done 134 minus 122. I'm so excited about it being 256. 134 minus 122. Realistically, I should not be doing this out loud, which is then only 12. Because 134 take away 122 is only 12. So looking at these 3 numbers, there's some like weird combination of them that I can calculate that gives me 12, which is then interesting because the value of the kind of discriminant of this, there's no b in the middle for this particular one, b squared minus 4ac. 0 squared minus 4 times 1 times minus 3 is 12. Hooray! Good. Matched up. I did get thrown by the minus signs, but very good. Right, okay. And the point being that I didn't need to work out the numbers, and in fact can't work out the numbers that you plugged in to get these. I can see them around the edge and did point at them. But I don't need to work out the numbers to work out the discriminants of the quadratic. So I've now convinced myself that wherever you are, without thinking about doing the transformation, or without necessarily believing that the transformation preserves the discriminant, I can work out a fact about your quadratic form if they're equivalent. Equivalent quadratic forms must have the same discriminant. Look at all this maths. Right, perfect. And then the question, which we'll come back to after a tea break, I think. The question is, given the other way around, given a discriminant like negative 260, for example, can you work out the possible reduced quadratic forms? Right on time. Thank you, Mary. It's time for a tea break. If you're joining for the first time, this is the thing that we do at about 3 o'clock. We take a break to go and make a cup of tea. I'm going to play some adverts, just because very slightly raises money for charity. But you're also encouraged to take a moment to look away from a screen, make a cup of tea if you want a cup of tea, or get a glass of water or something. Stay hydrated. Right, okay. As warned, there are now going to be adverts. You're not missing anything though, because the screen is going to say back soon, and I'll be muted till I get back with a cup of tea to engage with the question of the Converse question. That's the trailer. Come back soon for given capital delta, what could the quadratic form be? Let's do the opposite question together. Right, good. See you in a minute and a half. Right. Oh, I'm back. A surprise for everyone, including me. Am I unmuted? Did I do that as well? Oh wow, I pressed both buttons. Well done. Yes, I haven't been using this fact, have I? I haven't been using this Converse thing, or your lovely Desmos, which lets me highlight edges, so I can talk about which one I'm talking about. You managed to make them toggle between pink and red. It's impressive. That you can label the separated line or something between these. Good to see you again. Right, okay. Okay, previously on the stream. What are we doing? Previously on the stream. I'm back, I think I'm back. Whatever. Yeah, good. Okay. 260. So there's a couple of like clever arguments in here that I'd like to try and understand a bit better. They phrase this in terms of h, which is just for me a plus c minus b. Something to do with arithmetic progressions and values, and it breaks symmetry a little bit to think about two of the values added together minus the other one, but okay, fine. You can have it like that if you like. That's three of the values. So then, without loss of generality, oh no, but then no, same without loss of generality, h is even smaller, but positive. Let's go back up. All right, this is reduced form. I should understand this as well, I suppose. Add a source vertex for edge in the top of the graph of a positive elliptic form Q. So this is based on our understanding of what elliptic forms do when they have a source. And we got that by thinking about following the arrows, which I did. So okay, if you have to think about the arrows and following the arrows, then there are different cases, and in one of them, this is the one we're in, where there is some point such that three arrows coming out of it. Okay, fine, I will just take that for now. And then we're letting A and C be the smallest two, smaller two of the adjacent three. You solved this when you were in 12th grade. Ah, cool. I mean, what I'm currently trying to do is read a book that was updated last year. So maybe you could explain this to me in chat. That would be really helpful. Okay. Edge between them is labelled like this. Why is H positive? Why not? You can label them in either direction. Also, this idea that it's increasing as you move away. So, yep, I think we're taking one where we're moving outwards. Okay. A third of the values is like this. I would call this B, and the idea is that we've taken this to be the largest one. So I think I'm confused about what the relationship is between the discriminant of the quadratic form and the values that it takes at the source node, and the value lowercase h, which is the common difference of the arithmetic progression given by the values summing the two across an edge versus the ones on the other sides. Those things are all related to each other, but what I'd like to understand is how. And ideally I'd like to understand it in a way where I don't have to say the arithmetic progression across three of them, summing the two across the edge, taking the common difference between the terms of that arithmetic progression. What I'd like is, I don't know, something easier to remember. Okay, A and C. The smallest, yep, fine, and then that's the largest, and that's telling us that, oh, if you rearrange it, then H is less than A, even A. Okay. So that puts these in order. So where I would say, okay, without loss of generality, A less than B less than C, all positive, why not? Here, they've got three numbers in order, fine, okay. And if you've decided that given a particular value of the discriminant of the quadratic form, no, given values you get a discriminant, so any equivalent forms have got the same discriminant. So if you're looking for a particular if you're looking for quadratic forms that take a particular value of the discriminant, then looking at the values near that point, that's how you're going to identify equivalent forms. You might as well have it take those values somewhere else. That's what equivalent means. So you might as well consider the one that takes those values. I would probably have a B here. I might be using capital letters for the values. Or is it B? No, because I want that to be the value. Oh, that is clever then. That is clever, because you want the value to be a plus c minus h, which it does at 1 minus 1, or something like that. Yeah, that is quite clever. Okay, good. Oh, 24k guy is not explaining it to me. I thought they might. Oh, that's a shame. Okay. Do let me know if you've got this kind of link between. Essentially, why do they use this lowercase h rather than just talking about the values of the quadratic form? Since equivalence is defined by values, why are we thinking about edges and values of the difference of the arithmetic progression of the values at that point? Why don't we just have ABC? Why is h here? I'd be much happier thinking about b squared minus 4ac, for example. Ooh, hello. The top is made using a plus c minus h, a number that depends on the other two at h. Yeah, that's a description of what a plus c minus h is. Sure thing. The value h tells us how different a and c are from the top number. Yeah, you're talking about corners of a triangle. Yeah. I don't think we do want to find out how many different shapes have the same size. Do we? It's a topology book for starters. Oh look, here we go. Ah, it's happening. Brilliant. Is that, so when you say size, is that your size is then 4ac minus h squared? I don't understand that. It doesn't look like the size of anything to me. I don't know. Yeah, no, I don't know what you mean by size of a triangle here. Yep. You're just going to check all of them. Yeah, cool. So I'm going to read the textbook because the textbook has got rules for how I can check systematically, which is what I would like to understand. Good. Okay. So we've got these inequalities and we've got this rule. Find all equivalence classes and forms. We need to find all solutions. Right. And then there's a parity argument. Okay. Because of the form. Bound the choices for h by the inequalities. Here are some inequalities for sure, right? So 4h squared is less than or equal to 4a squared because h is smaller than a, and then less than 4ac, which is because a is less than c, and that is d plus h squared, which is just really clever, right? It's really clever because it tells us that h squared is bounded by d over 3, which is kind of too good, isn't it? So if you have a fixed discriminant d, or negative d or something for these ones, fixed discriminant negative d, like the one I just saw, did that have fixed discriminant? No, that had discriminant 12 rather than minus 12, but the one I saw in Desmos had discriminant, we could imagine one with discriminant minus 12, I suppose. And then we can find out if it exists. H squared has got to be less than or equal to d over 3, so we'd only have to check h squared being 0, 1 or 2. And also there's a parity thing, that h has the same parity as d. So if I'm looking for one with parity, if I'm looking for one with discriminant positive 12 instead of discriminant negative 12 instead of positive 12, then I only actually have to check the cases where h is 0 and 2. That's quite good. And I think if I check those, then what does checking them mean? Well, I still need to satisfy this equation actually for real. So I either need 4ac to be 12 in the first case, or if that's 4, then I need 4ac to be 16. So I'd be looking for numbers that multiply to give, in the first case, 3, and in the second case, 4. And there are some of those. So then maybe I'll be happy. Oh, but I need them to be larger than h. Good. It looks like I'm about to discover the quadratic forms x squared plus 3y squared, which is nice. That's got discriminant 12, minus 12. Mixing up my minus signs again. Yeah. Why is that broken? was going so well. Let's try reconnecting it. So the ones with 12. So there's this case where they multiply to give 3, but then a second case where h is 2, where the numbers need to multiply to give 4, while being each at least as large as 2, which I think is going to be the case 222. If we can imagine such a thing. That can be really small over there. Yeah, it's going to be really small. There we go. We're back on screen. That's good enough, I think. Cool. Yes. So the other case, I suppose, would be 2x squared plus 2xy plus 2y squared. Do I like that one? So b squared is 4 minus 4ac. Yeah, it's minus 12 as well. And I suppose the observation is that these have different values. So x squared plus 3y squared. Let's use the Desmos thing that shows us the values of these. Hey Fizzbuzz, good to see you. We are trying to classify quadratic forms given a particular discriminant, in this case negative numbers. Can you work out all of the quadratic forms that do that? Except when I say all of the quadratic forms, that's quite a hard task because there are loads that have the same discriminant. We're considering things to be equivalent if they take the same numbers. If there's some point where they take the same numbers, because from there they will take the same numbers out there. Quadratic form is something with x squared, xy, and y squared terms. And this one's got discriminant minus 12. You do the same thing as you do for quadratics. So you take the middle thing squared, in this case 0 squared, minus 4, first and last thing. So this one takes values like, just looking at it, giving it a visual once over, values like 1 and 3 and 4 and 7 and 13. You can see some patterns to these numbers that it takes. I'm going to switch off this separatrix because maths 2 to 2 has told me how to do that. Little challenge from chat is for me to say the right number of 2s when I say maths 2 to 2's username. The other challenge from chat is I have a PhD. How come I don't know everything? Oh dear. Right. Okay. And then there's this other one that we've discovered that has the same discriminant because there we go. Oh, loads of weird things happen there. The same discriminant. 2x squared plus 2y, xy plus 2y squared. So we're working by discriminant. The middle string squared is 4 minus 4 times 2 times 2 is minus 12 again. But this one's got totally different values. For example, it has a node which goes 2, 2, 2, which we didn't see on the other one. And it's probably not the case. I mean, all its values are even, which is nice. And it cannot take the value of 1. Not obvious when you first meet it, because you could make xy quite negative. Right. Maths 2 2. I've been trying to say it with 4 and then 3, which is more fun, I think. 2 2. But yeah, I had a lesson on Morse code a few weeks ago. Maybe I should do something in there. Amazing. If you're a PhD, name 3 theorems. Amazing. Bernoulli's equation tells you about pressure, energy. Sam Howson's making a video about it with hose pipes. It's going to be amazing. I'm going to dodge your question by not naming all of the terms. After you school, kind of I can't do Bernoulli's equation. Good. Okay. So we found 2 quadratic forms with different coefficients but all the same values. Let's go. And in the textbook they do this with an example with 260, where there's this bound on h squared, and h must be the same parity as d, so only a few cases to check. Time to calculate h squared plus d divided by 4, that's ac. Off we go, and then find some ways to factorise that. Okay, good. And then these ones, right, so then we're going to analyse what we found. So these are all different cases for different quadratic forms. Like we just saw that pair that are totally different, even though they have the same discriminant. So this is nice because then if you meet a quadratic form in the street or something, and you see 3 random values nearby, like this, I mean, you don't see what numbers have been plugged in. You just see, oh right, okay, I drew the diagram, and somewhere out there it took these 3 values. You could work out the discriminant and then say, well, is this the one that, it's either, based on the discriminant, it's either the 222 one or the 103 one, possibly with some transform. Maybe it takes these values near the origin. In which case, I suppose it would be something like, oh, I can work this out now. I suppose it would be something like 78x squared plus 26y squared plus, and then a bit more to give you the other term in the middle there. So on their own, these 2 small numbers add up to 90, 104, and there's another 90. So I think if I go 78, 90, 26, I think this works. 78, 90, and then 26. So obviously these are now huge. I think that's put this, yeah, there's the 194, brilliant. So this has moved this, this quadratic form, where I've had to work out these in a pinch or something, but this quadratic form looks super weird. It's got these numbers in the middle of the diagram somewhere. But because it's just a transform of the one that I showed you, there exists a point, can you see it on the screen, where it still does that 222 thing around a point. It has a point in common with actually any point of the previous one. It's just been transformed, it's just been moved around. So over here, look, here's the 222. And then arithmetic progressions, right? 2 plus 2 is 4, and then 6. And then that gives it 14. But if you see this quadratic form, it's sort of like, oh, which one's this equivalent to, right? You wouldn't maybe guess, looking at it, that it was equivalent to just twice x squared plus xy plus y squared. The technique we've got now is to work out the discriminant, 90 squared minus 78 times 26. And say, oh right, that's huge. Why do they think that would be a nice number? Minus 4 AC. Minus 4 AC, and like, oh right, okay, it's lovely, it's minus 12. That's not bad at all. Minus 12 is one we recognise. There's only actually 2 possibilities. It's either equivalent to x squared minus 3y squared, or it's equivalent to the 222 form. I'm not sure we've got a way of telling which of them it is at the moment, but we know reassuringly, somewhere in this picture we will either see 1, 3 and 4 around the vertex, or we'll see 222 around the vertex. In particular, this tells us the minimum value that quadratic form can take. Will either be 1 or 2. That's not obvious, right? Come on, that's not obvious. Once you've categorised them, you get facts like this. This quadratic form, which can take lots of different values, has a minimum of either 1 or 2 across all pairs x, y of integers. Does anyone have a separator line? I think I'm now thinking about plus 3y squared. At the moment, I'm thinking about ones like this, which also has, I mean, that's the other one that has discriminant. That's the other one that has discriminant. What have I done? B squared is 0 times 0. Also has discriminant minus 12. And because I'm in the bit of the textbook about elliptic quadratic forms, which is why I've removed all the separator line. Those are the 2 possibilities. It can't be the case that you can distinguish them by looking at whether they have a separator line or not, because given the discriminant, I think that tells you whether or not it can take... I think we did some like more basic categorization, right? To talk about whether the discriminant could tell us whether or not it had a separator line. So if they have the same discriminant of minus 12, then it can't be the case that one has a separator line and the other doesn't, which is a bit annoying. It'd be nice, wouldn't it? They have different minimum values, but they're both elliptic. Yeah, so there's this section 5.1 thing where we talked about there being 4 types of these. 4 types of these. Let's see. Yeah, so there were these. And did we do something to prove? Yeah, we found the separator line. Now, is it obvious to me why that's got negative discriminant? So, if it has some combination of positive and negative values, can we do something like thinking about... we've got all these formulas for the discriminant now, so it's quite tempting to think that we could just plug things in and look at the signs of different terms. Maybe not to be. Yeah, okay. Somewhere in here, though. What do? We looked at the edges leading away from this. Periodicity, don't. Is this something we're going to see? The sequencing in this book is sometimes a bit strange. It's possible that we haven't seen this yet. Where are we? So at the start of section 5, I think. Oh, frozen. There we go. At the start of section 5, we were definitely told this fact. But is it sort of we will see? It's a kind of we will see, isn't it? We will show later in the chapter. They're always doing this in this book. We're going to distinguish them based on their discriminant. But I think in the defence of Maths 2, we haven't seen that yet. I think it's coming up later. And even better, it's this. When you see that it's minus 12, you say that's 0 mod 4 or something like that. And then you know which one you're in, or something. There exists a form. Well, there exists a form is weaker than I'd like. I'd like to know all of them, really. Oh no, this is too easy. Right, okay, this is just there exists a form. The principal quadratic forms of these discriminants, but then there might be other non-equivalent ones. Yeah, I don't know how I feel about that. Okay, right. Back in, I think, because skimming through this talked about kind of general properties of the topograph for a bit, elliptic forms, but didn't yet prove to me that the discriminant separates the cases. Hello, Mean Machine Rex. You all right? Good to see you. We're having one of those streams. We're trying to do a lot of things. People in chat say hi to Mean Machine Rex, if you like. I don't really do that, do I? That feels weird. No. We're going to say hi to Mean Machine Rex. It's just got here. Good. There you go. Oh, right, okay. Oh, actually, this looks like proof. Yeah, maybe we've done this case. Oh no, this is good. I like this. What's this? It's telling me about delta. General considerations. This is what I want. Distinguished by their discriminants. Maybe we have seen this and forgotten about it. Positive non-squares for hyperbolic forms. Positive squares for zero hyperbolic forms. And 0 for parabolic forms. Okay, right, that's kind of what I wanted. But the roughly... you can distinguish between them based on your discriminant. So as soon as you see it's negative 12, you're supposed to say, aha, that's negative. We're talking about an elliptic form. Yeah, here we are. So looking at that elliptic form, think about source vertexes or source edges. Fair enough. Okay. With the label h equals 0, separating regions, source edge with label 0, followed by some other stuff going on. Positive labels p and q. I should draw it down here as well. Look, the discriminant is this, which is negative. For a source vertex with adjacent regions having positive labels p, q, and r, that's what this is pictures of. The edge between the p and q regions is labelled like this, and the discriminant is like this. But yes, so what they're doing is the sum of the squares minus twice the sum of the pairs. That formula that I've learned now for the discriminant of a quadratic form. When you're given 3 values around a vertex in the fairy diagram area topograph. Oh dear. Good with the entanglement, I liked that. Good. I forgot about stream. It's because I've become irregular. There was a good period of a couple of months where I was live every Sunday, but other things have been getting in the way. So it's good to be back reading about quadratic forms. Right, good. And then the triangle inequality came in. Yes, this is the bit I couldn't do in my head, I suppose. Exclamation mark. I can rearrange that. That is very nice, isn't it? I don't think I was in pain about networks. That's not fair on either networks or me, really. I I wanted us to see a proof of the Euler thing, and then we didn't do that. But that's just sort of my sensibilities versus someone else. And we did get on to talking about quite a lot of different things in networks. This gave me more things to put in the further reading notes. I think Mario Mario's a fan, right? I had a default student once to talk about networks. I think they could. Right, good. Okay. What am I doing? Parabolic forms, maybe. I'm reading about these. There's this amazing line of algebra here, which is just great. I sort of want to memorize it because this looks really nice. Something like if you have a triangle. Yeah. If you have a triangle, in fact, it's sort of separate from all of the quadratic forms things that are going on. It says if you have a triangle with side lengths p, q, and r, and you want to work out p squared plus q squared plus r squared minus 2pq minus 2pr minus 2qr, then you will definitely get a negative number. Can I make sense of that? Oh, hang on. That's starting to look like... If I make it into a triangle fact, can I make this into a triangle fact? Does this have some triangle meaning that I can then reinterpret and say, oh, you've got a negative quantity there? It's always the case that p squared plus q squared plus r squared is less than or equal to the sum of these, twice the sum of these pairs. That looks like a triangle fact. Right. It's close, isn't it? It's close. Could it just be AMGM in disguise or something like that? It almost looks like rearrangement inequality, except rearrangement inequality would tell you that p squared plus q squared plus r squared is greater than or equal to mixing them up. I think for positive numbers, maybe. And this result is actually that p squared plus q squared plus r squared, if they're the sides of a triangle, is less than or equal to twice this stuff, so it bounds it. And now I'm suspicious that looking at squares of the sides of a triangle feels like I've been here before with the squares of the sides of a triangle. Because don't you have something like the cosine rule on the squares of the sides of the triangle? Oh, I'm having fun now. Chat, I'm having fun now. Because you have the cosine rule, and all of these cosines. Oh no, I can't quite bound the cosines. I'm not quite there. But it's something with cosines. Did have a haircut. Don't think it looks anime. I think that's... Right. Okay. We're getting there. We got some like cos theta stuff, right? Or cos, what am I going to call that one? That's the third one, so we'll call it cos c. Is r squared. Right? That links together some of the ideas in this. So if you were given this as a triangle question, geometry, if it said p, q, and r are the sides of the triangle, prove that p squared plus q squared plus r squared is less than or equal to twice pq plus pr plus qr, you would go, where have I seen p squared, q squared, r squared, and 2pqs? Where have I seen those things before? And you would say, I've seen those things in the cosine, where have I seen them? I've seen them in this. Expressions like this, which is then nice because it gives you things like p squared plus q squared minus r squared is equal to 2pq cos c, and symmetrically, and then I guess you could add those. And you would get p squared, a p squared, and a minus p squared. So you would get, if you sum them, p squared plus q squared plus r squared is equal to, in a triangle, 2pq cos c plus 2PR cos B plus 2QR. I'm really small down here, aren't I? Cos A. Oh, that's tiny. Sorry about that. Right, okay. But that's not quite what I wanted. So that's a kind of cosine rule fact about what that sum actually is. I'd like it to be. I've been distracted by this triangle rule. Triangles. Love triangles. What geometry, please? All this topology, and I'm just like, a geometry fact, hooray! Measuring triangles, yes please. Telling me that the triangles are all glued together at their edges. It's not going well though, because I've got all these cosine factors in. But I think all of those cosines might be less than or equal to 1. That would do it, wouldn't it? Those would be less than or equal to 1. And then I'd be done. Yep, triangle fact. It was the cosine rule in disguise. Oh, I thought it wasn't close, and then I realised what to do. These cosines are all less than 1. So we're less than 2pq, 2pr, and 2qr added together. I think we actually did it. Yeah, cool, good. So you can prove this, or you can so you could do it using cosine rule facts, or RFL, or you can rearrange it like this, which I'm never going to understand because where has this come from? It's amazing. Look at this. It's nice and symmetric, isn't it? Ooh. And it's got those squares in, and then it's got minus stuff. I guess you sort of split these out, and then you refactorize it into these three. It's all going on. Right, good. RFL. Reflexivity. We had a thing, we got the thing. Those are the same, so we're done. Except I haven't quite written out the thing that I said out loud, but never mind. Good. Okay, excited. So when I see the sum of the squares minus twice the sum of the pairs, a little part of me is going to think, if your numbers form a triangle by doing triangle inequalities, then mumble mumble cosine, mumble mumble, you get a negative number. Good. Why do the things do the triangle inequality? I feel like that's a special property of elliptic forms. And we define those as ones that only take values of a particular sign. So it's something like you get this source node and you're moving away from it, and because you're moving away from it, you get larger values, I think. And that means that the difference in the arithmetic progression of the values in the regions of the topograph of the Fourier diagram is positive. So P plus Q is bigger than R. Triangle inequality. There's just so many words to say now. We've got so many words. Oh, okay. I think they've gone, which has saved me from deciding whether or not to ban them, which would have been a tricky choice. Yeah, so I should probably prove the triangle. Well, why do triangles do the triangle inequality anyway? I suppose over here I'm not using the triangle inequality. I'm sort of avoiding the triangle inequality and using this cosine fact instead, from which you could deduce the triangle inequality. If you believe in the cosine rule more than you believe in what triangles look like, then, if you don't want to say, well, clearly this line is a shorter distance than going via this point, if you don't want to talk like that, we say, well, I believe in the cosine rule. Always start with the cosine rule, and then you can bound things and say, aha, so therefore this thing is bounded by p plus q squared and p minus q squared, and it is r squared. So this gives you a bound on r. Right, we've accelerated for some reason. Did I get cross and get better at maths? Would be an interesting thing. Interesting effect. We should study this more. I think I got my back up and then became less chill. Oh no, less chill and better at maths. Are these things in contrast? No, it's fine. It's fine. I can chill. Right. Yeah. Good job moving chat through as well. Good. Right. Yeah. We're all in this together. Right. Good. Okay. We're maybe going to think about parabolic forms as well. Parabolic forms. Chocolate coins on string. Parabolic forms. But those forms have got a region labelled 0. At which point, a region labelled 0 would make me think some of the squares Well, hang on, if I plug it in here, if one of the regions is 0, I don't obviously get... Oh no, hang on. If one of the regions is 0, I get r squared. And I get that 0, that 0. So I end up with p squared plus q squared minus 2p cubed. I know that expression. That is p minus q all squared. So that looks like a positive square. What are they going to tell me in here? Oh, they told me it's 0. P plus q equals a 0 now with this parabolic form. Okay. Right. Oh no, there's also this thing called a 0 hyperbolic form. I haven't understood the distinction there at all. I have to go back and look at the distinction there. Chocolate medals. Sorry. That's the one I've just described, where you have a region labelled 0. So these parabolic forms have got an extra restriction, I think, that as well as having a 0 region, the ones nearby are sum to 0, which I suppose in terms of an arithmetic progression would then give you like a 0 difference or something in your arithmetic progression. So I'm missing what these parabolic forms are. I'm just going to go back to the start of the section and look at what were those. I haven't been thinking about them at all. I see. A bit interesting, I suppose. Like medium interesting. Yeah, down here. What are these? Oh, we're going to look over here. Here is the summary of what these things are. So I haven't not been paying attention to the second and fourth of these. Positive and negative values, and also the value 0. Okay, so it's got a region of 0. Yeah, fine. Okay, so that's quite a general class. It's got these ones in where the discriminant could be some positive square. Positive square? Positive square, 100. And down here, value 0 and either positive or negative values, but not both. Right, okay. So I still think that's got a region of 0. But then, so then this technology about labelling the edges is apparently how we're going to distinguish between these ones. The parabolic ones turn out to actually have discriminant 0. Check it down here. Yeah, down here. So the distinction here is whether you get 0 or some other square. How many regions labelled 0 can you possibly have, right? So I suppose if you have 3 all at a point, then you're going to get loads of zeros. That one maybe doesn't count, that's the 0 form. Oh yeah, equivalent to the 0 form, I'm pretty sure means 0 because it's going to be 0 everywhere. If you've got 2 regions labelled 0, ooh, what's this going to be? 2 regions labelled 0, but you could have some value over here, which would then give you this value over here. So if you've got 2 regions labelled 0 next to each other, then I think you could still have some values, right? We could go and infer some more values over here. So 0a, 2a. This is looking fun. I don't know what else is going to go on. 0a, 2a over here as well. This one goes 0, 3a, so 6a. Well, you know, it's doing stuff. Negative values over here. Doing stuff. Is that going to be... So that's 0 hyperbolic, I think. You can be 0 in 2 regions, but have some difference on your... some difference to your arithmetic progression, negative a, 0 plus 0, a. It's so annoying trying to read about this arithmetic progression. I need some words to describe it. It's minus a, and then the sum of these two values, and then that one. They form an arithmetic progression. Sort of central fact about values on regions of the topograph of the fairy diagram. Right, is it equivalent to that? Quick check. That one has got discriminant b squared, a positive square. It's not obvious to me that all of the ones... Is this thing on the board equivalent to bxy? Yes, because bxy does have a bit near the middle of the picture where you have in your regions 0, 0, b, minus b. So the thing I've drawn at the bottom here is equivalent to the one you've put in chat. Yeah, okay, so if it's got 2 zeros next to each other, it's equivalent to that one, and that's a 0 hyperbolic form. because it can take the value 0, positive and negative values. If it's got 2 zeros in totally different places, we've been through some of these cases, I think, in the textbook, but actually going through all the details was quite hard. If it's got 0 in 2 different places, then I suppose you want to look at near one of the zeros and then argue about what's going on near there. Have we seen ones with exactly 1 0? So is this the parabolic forms that I'm interested in now? These parabolic things where... So I'm a bit interested in what you put down here. And I think it's telling me that in order to avoid having negative numbers, I have to put negative a here. Which is a bit surprising. The things around here have to add up to 0. Which is then going to give me 3a over here, which is unlikely. Then they would have opposite signs. What are we talking about? Right, yeah, so I've not understood something here, because I would have thought that, here's what I can't piece together. If it takes 0 and only either positive or negative values, but not both, then I think it's got a vertex where the values are like this, a, b, 0. And then I think, so question mark 1, I think this means it's got a vertex like this, near the 0. Vertex on the value 0. And then question mark 2, I think that means that delta is the sum of the squares minus the sum of the pairs. So a is greater than 0, b greater than 0, let's say. Think about this one first. The sum of the squares minus the sum of the pairs, twice the sum of the pairs, would be a plus b squared, which I think is non-zero, because a and b are both positive numbers. Even if one of them is 0, I don't think both of them are 0. Both of them 0 would be mad. It would be all zeros, wouldn't it? Everywhere from there on. 0, 0, 0, 0. Reading outwards. So even if one of them is 0, I don't think I want both. Also, we just thought about ones with 2 zeros next to each other. I don't want that either. So I think A and B are both positive. And then I'm confused, because now I think that delta is... So now I think delta is positive. But down here it says delta is 0, in this case. You see? I've got these question marks. There's a step I don't understand. There's a step I'm wrong about. I wonder which one it is. Probably it's going to be this one about the calculation of the discriminants. Which is a shame, because I put quite a lot of work into working out the discriminant based on the values. We were pretty sure that it was going to be the sum of the squares minus twice the sum of the pairs. Minus twice the sum of the pairs? Or minus once the sum of the pairs? There you go. Oh, we saw this PQR. We just saw this thing about p squared, q squared, r squared. But when I did it for that calculation with 120, didn't I have 134 minus 122? I did double the... Did I double the sum of it? Because I had 22, 35 and 6 was 51 double to a... No. Let's get this right. Let's get this right. What step am I getting wrong? X squared plus 3xy has far away zeros. Let's have a look at that. Seems good. Mary believe that we're going to... Oh, I see what you mean. Zeros in different places, right? So I can see a 0 here, and it's got another one over there. So you can have a couple of them. And it's got a discriminant, b squared minus 5c, 9, which is positive square. Right, so what am I misunderstanding about this discriminant fact? I think I saw somewhere in here that I had this big formula for the discriminant. It's over here, I think, with the values. Yeah, sum of the squares minus twice the sum of the pairs. So if you had, and this is the calculation of the discriminant, right? Yeah, I should look at some examples of these, shouldn't I? Let's look at x squared. I like this idea of looking at examples. We've got your calculator for them, so might as well. We've just got a single 0. Right, so then I'd have guessed that these would be plus or minus of each other. I'm wrong, they're both 1. So yeah, there's the boundary of my understanding, right? I thought that these would be 1 and minus 1 because I thought the discriminant would be 0. The discriminant is 0. It's b squared minus 4ac, which in this case there's no b and there's no c, so b squared minus 4ac is 0 minus 0. So the discriminant is 0. The discriminant is not sum of the squares minus twice the sum of the pairs. Wait, yes it is. Minus 1 plus 1 minus 2 times 1 is 0. What is going on? Right, okay, because they're both positive numbers. So I thought a squared plus b squared minus 2ab minus 2ab minus 2ab minus 2ab. You find this is an important thing. I know it looks stupid, but this is an important thing. But you find as precisely as you can the bit where you're wrong. And then you stare at it until you work out whether you've made an interesting mistake or an uninteresting mistake. And in this case, I've made an uninteresting mistake, I'm afraid. But it's forced me to think about things. So it is important either way. Right, did you spot it? On screen. Here it is, it's not a good mistake. A squared plus b squared minus 2ab. It's a minus b squared, not a plus b squared. Which could be 0. Especially if a is equal to b, like we just saw. Does that start with a 1, 1, minus 2 or something? So it doesn't lead on to this. That's the literal, glad I recorded it. I can watch that back now. I have a little recording of me realising that the sum of the squares minus twice the sum of the pairs really was 0. Great, I'm having a time there. Maths to do in chat. It's got there. Okay, good. Right. But in fact, we're told further down here that a minus b squared, this discriminant is 0. So now the next bit for me to understand is I'm being told that in this case, those two numbers must be the same. I suppose I'm looking at the positive case, and with the fact I'm being told that they must be the same, otherwise I'll get some negative values. And I suppose it's looking over here or looking over here. Because if A is larger than B, then I have, walking, which way am I looking? Might have drawn those in the wrong places. If A is larger than, if A is smaller than B, then I've got A plus 0 is A, and I've got B which is larger, so then this will be smaller. And then I could keep walking and keep going down smaller and smaller numbers in an arithmetic progression around here. So in fact, is it the case, and if they go the other way, then I could keep walking the other way. So in fact, I think all of these numbers around the 0 must be equal for a parabolic form, because if they're not equal, then they set up a chain of, because I'm adding 0 to each of them, they set up a chain that, we've seen this picture somewhere in the notes I'm sure, they set up a chain which would just be linear, and decrease to 0. So I think in this x squared picture, if I look more closely, around the 0 there are in fact lots of 1s all the way around. Is that true? Yeah, look, all the way around. 1, 1, 1, 1, 1, 1, 1, 1, 1, all the way around. 1, 1, 1, 1, 1, 1, 1, 1, 1. Great, okay, so they have to be equal. So there's a good reason why they're equal. In order, and since it's always positive around the 0, as you keep going. Okay, good. So I think I understand this delta equals 0 case. Should we do a non-trivial one? Right, so the logic is something like, I just have to make sure that b squared minus 4ac is 0. And I should try and do that in a non-trivial, way. So I'm going to make b squared be something that includes some 4 by making it b squared be like 6 squared. So if I do that, not done yet, because currently the discriminant is b squared is 36, and then minus 4, so minus 4 ac what shall I do there? So I want to get down to 0. They've got to multiply to 9. I think I'll try to sort of break symmetry or do something non-trivial by putting a 9 in here. And I think that is parabolic. Yeah, it took me a while to find it, but there's a 0 over here. And then in this case, it's 1s all the way around the 0 again. Maybe if I put 3s in here, that'll be more fun, because now there'll be a 0 somewhere with 3s all the way around it. It turns out. Good, okay, so these have both got discriminant 0. Ooh, yeah, they've both got discriminant 0, and they're not equivalent to each other, because I suppose the way I would characterise them is something like the numbers around the 0 all have to be the same. And, well, they could be different. And that categorises the parabolic quadratic forms, because once you've decided what you're doing around the 0, they're all the same, so now you've got 3 numbers at a point. And 3 numbers around a point with 1 0 always has, equal 0, always has a squared plus b squared minus 2ab cancel out to give you 0. So it's exactly 3 times. Yeah. So I think because of that, so here's the chain of logic then. If you have discriminant 0, we don't understand this quite yet, but if you have discriminant 0, you must be a parabolic form. That's the converse of a thing that we've just been talking about. We've been saying if you're a parabolic form, you must have a 0 somewhere. It turns out, I think, that if you have discriminant 0, then if you have discriminant 0, then you're a parabolic form, which means you have 0 somewhere and you have a constant value around there. Based on what that constant value is, those are the equivalence classes of these quadratic forms. Ones with the same number around are the same as each other. And then as you've spotted, well, obviously, I suppose, if I put a larger number here, like 30, then it's just going to make everything 10 times as large. So really, there's only one idea here for a parabolic quadratic form, multiplied by some integer. And that integer that we're multiplying by is, you could think of it as what's next to the zeros. What's next to the singular 0. And then it always has the same structure, that the next one around is 4 times that. And over here is, what on earth is that? I suppose it's 9 times that. These squares, these look a lot like squares because the only idea on the screen at the moment is x squared being a quadratic form. You could certainly include it in your list of things that look like ax squared plus bxy plus cy squared, none of that. And so it's this, but multiplied by 3, or you might as well multiply by 30 or something. This tool's great, thanks for building this. This is really good for visualising quadratic forms on the topograph of the fairy diagram. Right, love it. Yeah, discriminant, okay, here we go. If it has discriminant 0, the root of the quadratic is repeated. Yeah, okay. Oh yeah, you can think about the roots. Yeah, I wasn't thinking about roots. The root is repeated. That's you working out where is 0, which is only one place. Yeah, okay, good. I like that. It's more direct. Yeah, you can work out where it's 0. If it has discriminant 0, it's got a repeated root. Lovely. Which is rational because... Ooh, now I'm worried. No, I shouldn't be worried. It's rational because b squared minus 4ac is 0, and then the quadratic formula gives you the value, and it's rational. It's minus b over 2a or something. Good. You get a rational point. So there's some rational point which you can plug in and get 0 back into your quadratic form. Like it, nice. Yeah, there you go. You've told me it's b over 2a. I've said quadratic formula. I look silly now. It's rational because of the diagram. Great. Yeah, good. And then everything around that depends on the magnitude. So what are these? These are just squares, aren't they? Of course they are. I'm squaring x. Square of the numerator. Cool, good. Okay, I would say that we've now understood parabolic forms and appreciated the difference from 0 hyperbolic forms. Now we can jump quickly back in. We're about to hit 4 o'clock, but I'm going to roll slightly over. I thought I was going to do a short stream today because I was a bit tired, but streaming is really waking me up. Here we go. Was that the proposition? Yes, distinguished by their discriminants. Hence the name, sort of, maybe. So if there is exactly 1 0, No, I think you can be. Zero hyperbolic with exactly 1 0. I think, because I think you can take a value here, and then I think you can be fine. So let's try it out with setting up a 0 hyperbolic thing, but with, so you gave me this one, which has got 2 zeros. I think I can set up a 0 hyperbolic thing with exactly 1 0. What's the other root of the quadratic going to be? Interesting. What is the other root of the quadratic going to be? What am I trying to do here? Yeah, okay, maybe I can't. Because if you get a repeated root, then you have discriminant 0. And if this quadratic has, what am I trying to claim? The quadratic's got exactly 1 rational root. Good luck me. Yeah. I think you're right. The book goes on to, so we're about a third of the way through the book, and the book goes on to do pretty incredible things to do with prime numbers. So I would quite like to get there at some point in my life. It's not obvious that we will get through the intermediate pages to get to that. And then there is the big napkin book, which has all of maths in it or something. Over 1,000 pages of all of maths. Yeah, I think I'm with you. Ooh, peek the microphone. Good. I think you only have 0, because you could not be 0 anywhere. You could have 1 0 if your quadratic has a repeated root. We've seen that. You could have 2 if your quadratic has 2 rational roots. And then you could have infinitely many, because what's the thing with infinitely many then? I mean, the 0 form does that, but have we seen that we've seen things like, no, can you have infinitely many zeros? Where have we seen that? Do you mean like along the periodic line or something? Oh, you mean the 0 form, right? Yeah, we've seen something with. Yeah, I was worried that we were going to have to look along the separator line, but I've realised the separator line only applies to one star. Don't take the value of 0. Good, right. That is like a regular quadratic, if you include some degenerate quadratics in your list of quadratics. Right. What do I want to read? I want to read this last bit of this distinguishing. We can go back into the enumeration of how many cases you've got, which is where I thought we were going to go, but we've actually gone backwards. Which is fair enough. I feel like I understand the cases a little bit better this time. See that this is not a square. Oh, edge in the separator line. Supposed to forms like this. A must be non-zero, otherwise the form would have the value of 0 there. And similarly for C. If the discriminant was a square, then the equation would have rational roots. So it's just telling us about these rational roots. By the familiar quadratic formula, this. Oh, right, okay, so it would be like that. I would have the zeros. Yeah, fair enough. I get the stuff we were doing. Right, okay. Alright, wow. Evan Chen also streams on Twitch. Evan Chen does sometimes Olympiad maths. Let's see if we can find Evan's handle. Is it Evan C? What's your handle, Evan Chen? Is it Ven Hans? Yes. Let's go. Also check out, I mean, this is maybe like telling people about something they're already aware of, but there's this incredible stream. Oh, wait, what is that Twitch channel? Let's actually get this right. Oh, it'd be amazing if they were live, wouldn't it? If they're live. Okay. Let's check. Are they live right now? I think they're not. They're not live right now. But also check out someone who's way better at maths than me. If the person who thought I wasn't good enough at maths is here, like you're like Evan. You can catch Ven Hans when they're live. Next live appears to be on Saturday, so you can catch them. Good, right. Okay. Does the number of zeros determine what type of form it is? I think it does. Because I'm pretty convinced now the ones with 1 0 have a rational root that is a repeated root, which I'm pretty sure makes them the parabolic sort. The ones with exactly 0 zeros, yeah, I think they're the elliptic variety, and the ones with, oh, do I mean that? Yeah, I think I do. No, maybe it doesn't determine what form, because I think that could also be a hyperbolic sort, but not a zero hyperbolic sort, which take 0 exactly twice, but not infinitely many times. And those, what do I think? You showed me that example with 2 zeros that were far apart. Yeah, okay, good. Right, okay. Characterizing. Yeah, I think I'm worried about, does the number of zeros actually tell you precisely which one you're in? Because I'm not sure I have enough cases, right? If you remove the infinity case, then I only have 3 cases, 0, 1, and 2. And I think there are 4 sorts, so pigeonhole principle. There we go, that's got me out of thinking. Yeah. I think it'll be the distinction between whether you have complex roots or irrational roots that we should worry about quite a bit. The irrational root case is probably going to give you some sort of separated line effect. We've seen a separated line for, what am I talking about? Whatever. Okay, good. Yep, we're going there. I think we're going to follow the separated line to our irrational root of the quadratic. That sounds like fun, doesn't it? And it will be a quadratic sort of shaped root, so it'll have some nice. We've proved that periodic fact. Should give us facts about continued fractions of things like square root 2. Yeah, it was the irrational roots that the separated line ones. The complex root ones don't show up. They don't have any roots. So you get single signed. You get your quadratic form is kind of single signed. I'm imagining here looking for roots, dividing by y squared, so that I'm looking for x over y as a root of some normal garden variety quadratic. I think that's allowed. If I'm searching for roots, maybe I shouldn't talk about single signed. I should talk about just looking for roots. Yeah, okay, good. Right. Looking at the sign of numbers and also trying to talk about complex numbers in the same sentence is probably bad. Oh, there's the thing on the board. There's a number of times I think I've had an idea and it's just also there. Yeah, there you go. Is this actually telling me about how many zeros there are? Okay, I mean, it's telling me that hyperbolic forms don't take the value 0 by definition in this book, I think. Good, right. I'm stopping the stream, I think, as the sign-off phrase goes. Do check out other math streams. There are several now. Well, there have always been several, but the one I'm thinking about is that I'm pretty sure Cat Does Maths is back. Let me double check. Fact check. Are they live now? No. Oh, I found out about raiding. Have they got a schedule? They do have a schedule. They're back on Tuesday. Let's link to them as well. Also check out Cat Does Maths. These are again people who are more famous than me, but I kind of feel like some of my followers found me from something else that wasn't Twitch. So you might not be aware that there are bigger math streamers on Twitch. This is like the gateway where you're like, yeah, you found me from like some Oxford thing or something, but are you aware that there are actually people already here? It's like Numberphile, right? It's like telling people that Numberphile is a thing. It's like, if you haven't found out about Numberphile yet, then you might find out about. You might like to find out about Numberphile, but it feels silly telling people. You might not have heard of this. There's a YouTube channel that has really great videos. Oh, right. Good. Right. Okay. Have a great week. I will be here next Sunday? Question mark. I will be here next Sunday. Full stop. I'll see you then. Yeah. Yeah, you might like. Should we do a link for? There's also other people out there. Great. Let's not try and list all of the maths YouTubers and maths Twitch personalities. Let's just call it a week there. Right. Next time, more understanding of quadratic forms classified by their discriminant. We would like to see the converse question. Given a discriminant, can we find the quadratic forms? We are pretty close to just doing it, I think. The textbook's done one case. We're going to look at the next case soon. But I'm stopping the stream now. Bye.